Hi, in this video we're going to give an overview of the simulation plugins in GDS Factory. So you can read more about the simulation plugins on the documentation. So we're going to show one example for each of the plugins. So first we're going to start with MPB mode solver simulations. Then we're going to do Meep FTDD simulations of the components. And then we're going to take those components and connect them into a circuit to do a circuit simulation. And for that you can either use any of the open source ones available. I'm going to show it with Symphony, but the same thing could be done in SAX. The nice thing of Symphony is that we will be able to show also like a Monte Carlo circuit variability, similar to what you can see here. So you can go through the tutorial. You can also read the API. So on the API, if you go to mode solver plugins, you'll be able to see what are the functions available for these mode solver plugins, as well as the FTDD simulation plugins, as well as the circuit simulation. So without any further ado, let's get started. So I have downloaded this. Basically, you need to install the GDS Factory, and you need to also install the UBC PDK. So this one, we're going to simulate some of the components from the UBC PDK, which is an open source PDK available on GitHub. Both of them are in the GDS Factory organization, so you will need the UBC PDK and you will need the GDS Factory PDK to run these examples. So let's start with the silicon refractive index, and let's compute the mode of a strip waveguide, like a fully edged 500 nanometer waveguide surrounded by oxide. So you can see the modes. So this is the first order mode, the fundamental T mode of the waveguide, which has an effective index of 2.44. Now we import the UBC PDK because we have the K-Layout GDS Factory plugin installed. And we can also see as we run examples or components, we can see them also in K-Layout. But you don't need to leave the notebook environment, but just so you're aware that you can do both. So this one has a splitter, has 3 ports. So before you run an FTD simulation, it's important to make sure that the simulation looks correct, the port monitors are correct, that the ports extend over the PML. So you can see here in red you can see the port, the source, and in blue you can see the monitors. So I'm gonna run the same thing with running const true. It's gonna be very fast because we're using a file cache, which means that the simulation has already run before, so it's gonna grab the simulation results already from the file. So you can see here it's loaded from a path, and you can plot them. You can see it's roughly it's a 50% power splitter, so we get around roughly like a 50% of the power at 1550. It's a bit it loses an extra dB, but you can also, so this is a full 3D FTDD simulation, but you can also do a 2.5D, which is less accurate but it's much faster because you're simulating a problem that it's 3D but you're collapsing one of the dimensions, but doing an effective index approximation. So you can also do this, and you can compare both basically the 2.5D versus the 3D. So the 2.5D gives a little bit lower loss. Another thing you can do, you can exploit port symmetries. So basically these are to save computation. So for example, you have this bend, you can also see the bend here. To compute these parameters, you will need to do 2 excitations. So you will need to do 2 simulations, each of which needs to have the port at the source at a different port. But because we have kind of like a symmetry, we can also use this function called a 1x1, which will basically exploit the symmetries of the S parameters, and this will basically save the simulation. And this is how you will define it. So for port symmetries, even better than a bend is to use a crossing. So a crossing, all the 4 ports are completely symmetrical. So you can actually export the port symmetries of a crossing, where you only need to basically do one simulation and you can get the full excitation. So you can excite only one port, and you can get, using the other 4 port monitors, you can get the S11, which is the reflection, S1, let me see, S13 will be the transmission, and S12 and S14 will be basically the crosstalk of the crossing. And yeah, we can do the same thing. We can see here it's also very fast because we are using the file cache. I mean, first we're running with false, so this is just to visualize it looks correct. But when we run with true, you will see that this is very fast because we have run the simulation before. But if I change any parameter, like I change the resolution or any other thing that makes the simulation different, this will take like a few minutes to run. But this is very good to have it for like a demo purposes. Where we have also the instantaneous response almost. So at 1550 you can see that this crossing losses are in the order of 0.5 dB. So this is the transmission. But you can port any other parameter. So you can see this one. It has roughly like -25 to -40 basically back reflection. So you can choose. Another thing you can do when doing this large-scale simulation is to use multi-core, where you divide the problem into multiple cores and speed up the simulation in that way. So here we use MPI to run the simulation of a coupler. So a coupler is basically a 4-port devices where you evanescently couple the light from one input to another output. But there's also some light that goes straight, so this is the through and this is the coupling port. So, and depending on the gap and the length of this propagation, you will have a different amount of coupling. So you can have this from 0 to 100% coupling depending on these values and depending on the wavelength. And you will see here that we're running with 4 cores. So this we're doing the same trick here where we're running with a file cache. You can see the files already exist, so it just grabs it from the cache, and you can plot the S parameter simulations there. Let's do a batch simulation. You can also run a batch of simulations. So a batch of simulation basically runs multiple simulations in a queue in multiple cores using MPI. So we're gonna do an example of just running on a straightaway gate, and you can see that, I mean, this is also very fast because of the file cache, but we could in principle distribute this in different simulations. So we use 8 cores and we use only 4 cores per every simulation. This will allow you to run two simulations in parallel, and if there is more simulations than cores, it will basically queue them. And this is also for a ring coupler. So you make sure the simulation is correct, you run it here, and then we see these parameters. Something maybe also useful to do is to run these as simulation markers. So directly on the layout you can see where the source and outputs are. So for that we basically put similar colors that Meep uses. So we use blue for monitors and red for source. You can also render in 3D, so you can see your layout. In this case I didn't put the colors of the marker, so they are black, but you can change that on your layer stack. And finally, what we're gonna do is we're gonna take the simulations. Basically, we're gonna take the different S parameters of every component to simulate a max and interferometer. So for that, first we're gonna do it with Symphony. So Symphony, it's based on Scikit RF, and it's an RF package. And we're gonna take this Y splitter. We already simulated the S parameters. On that Y splitter, we're gonna take a bend and a straight. So using 3 components, we can simulate a complex circuit. And in this case, this complex circuit is an MDI which has 10 micron imbalance between top and bottom arm. So it's gonna show spectrum. So we're gonna simulate the spectrum from 1550 nanometer to 1600 nanometers. And then you will see that it has some wavelengths where destructively interferes. For these wavelengths, it will accumulate more phase on the bottom arm, which is longer, and it will destructively interfere. If we increase the delta length 20 micron, you can see it double here. You can see basically it doubled the length here on the bottom arm. You can see that you can also use the same circuit model with different values. In this case, the straights here are longer. So because we double the delta length, the FSRs will be half of it. And finally, we can take into account like variability of the group index of the fabrication process. So due to fabrication and wafer variation, so there's basically width and height variations across the wafer. Your foundry is going to have a sigma effective index, a sigma group index, and sigma dispersion. And if you get these values from the foundry, you can actually run like a circuit Monte Carlo. So in this case, it's running 10 simulations of the circuit. And in this case, it's changing the model of the waygate to take into account this group effective index and an ineffective index variation. What actually really matters for this kind of like interferometer is the group index, which is the delay that suffers the light through it. And you can see that the MPI spectrum now is all over the place. So there's different colors every color represents a different run. And that shows that your filter can be anywhere within the FSR. And finally, the last thing is that we're gonna show you how to do this also with SAX. So with SAX, you need to have the GDS Factory version. And actually here you need to, instead of this one, you need to use SAX read model from CSV. So this is basically you have your same idea. We have the models for every of your components. We define the net list of the circuit, and then we can simulate basically the spectrum. And here you can see the spectrum. And we can also do the same thing for a different circuit where we do, instead of 10 micron, we can do 20 micron. And you will see we can copy paste this here. And then let's do a 20 micron. So you can see here delta length equals 20. And we do the same thing here, so we only need these 2 steps, because those are where we get the net list from, and then we need to plot it. So we're gonna see the same thing. That basically because we cut the length. I forgot to add here MCI 20. So this is MCI 20, get net list, and then we simulate it. And here you can see too that the FSR is half of what it had. So what we've shown this factory documentation. So what we've shown is that we've shown like an overview of the simulation plugins. So we have started with the mode solver. We've shown MPB mode solver. It's similar API for the 3D mode solver, which is also open source. We've shown the FDD simulation using Meep in this case, that we simulate the S parameters of every component. And we have connected the S parameters of each component into a circuit using both Symphony and SAX. So I hope you find this helpful, and let me know if you have any questions. Thank you.